Hello everyone, welcome back. Let's talk about another hard problem on Leetcode today. Word search 2, Leetcode 212. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. We have already covered part 1 of the problem, where we were given m into n board of characters and a word, and we had to check if the word can be found on the board. However, in this problem, instead of one word, we are given a bunch of words. And from these words, we should return all words that can be formed on the board. Each word must be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. And the same letter cell may not be used more than once in a word. Let's take an example. Given this board and this list of words, oath, eat, pee and rain, we can find oath and eat on the board, but we can't find pee because there's no P on the board, and rain is not possible because the letters aren't sequentially adjacent. And note that we are allowed to use the same letter across words, but not in the same word. For example, the same letter T is used in both oath and eat. And since we found the words oath and eat, we will return a list containing these words as the answer. Now, in terms of solution, the most straightforward or naive approach will be to simply reuse the solution from the original word search problem. We can iterate through our list of words, and for each word, we perform a completely new search on the board. So, we'll start with the first word from our list, which is oath, and we scan the entire board to find its first letter O, and we find it at the very first cell at index 0, 0. And with this as a starting cell, we trigger a DFS to explore all adjacent cells, up, down, left and right to find the next letter, A. Now, to ensure we don't reuse the same cell for the same word, we'll use backtracking. We mark the cell as visited before exploring its neighbors, and then unvisit it after the exploration from that path is complete. So, we visit O and try the search for A in 4 directions. We can't go up or left, as that will result in an out of bounds error. And if we go down, we see letter A, which doesn't match the letter A, so we backtrack. But on the right, there is an A, which is a match. So, we visit this cell and start the 4-directional search for the letter T, which we find by going down. All other paths from A would return false. From here, we search for the letter H, which we find by going down again. And now that we are at the end of the word, that means we could find the entire word, and hence we add it to the answer list. Next, we would then repeat this exact same process for P, then eat, and finally rain, where we'd find eat, but we would fail to find P or rain. Now this approach works, but it is very inefficient. The time complexity to find a single word of length L is roughly O of m into n times 4 to the power of L, where m into n is the size of the board. We have a factor of m into n because, in the worst case, we might have to start a search from every cell on the board. And then, since we are trying to find a word of length L, the depth of the recursion is L. Each cell can produce up to 4 recursive calls for 4 adjacent directions, leading to 4 to the power of L calls. Since we have to do this for every single word in our list, let's say there are W words, that adds a factor of W to the time complexity. That means the total time complexity now becomes staggering O of W into M into N into 4 to the power of L. So, we need to find the better way. The brute force approach has a major bottleneck: repeated work. Imagine our word list is apple, apply and apples. Our naive solution would first search for apple, traversing the board. Then it would start a completely new search for apply. Notice that the prefix appl is the same. This means we are doing the entire search for APPL from the scratch. Then we do it all over again for apples, re-exploring the same paths for these common prefixes. And this leads to a big question. What if we could flip the problem around? Instead of searching the board for each word, what if we could search the board once and check against all words simultaneously? And since we are dealing with prefixes, a brilliant data structure that comes into play is the trie, also known as a prefix tree. A trie is designed for this exact problem. It is a tree-like data structure that consolidates all words in our dictionary based on their common prefixes. So, instead of having the separate strings, the trie weaves them together. Now, when we trace a path on our board, like APPL, we can look it up in the trie and see all the words that start with this prefix. And this is what we needed. And now, we are going from searching one word at a time to searching all the words at once. So now let's see this with an example. First, let's build a trie from these words. In trie, we start with an empty node. Think of it as the starting point of all our words. And then we insert apple. So we add a node A to the root, then a child P from A, then we add another P, then L, and finally E. And to remember that apple is a complete word, we mark the final node E with is end of word flag set to true. And visually we can see it with a star or asterisk. Next we insert dog, and dog doesn't have any shared prefix with apple, so it gets its own branch from the root. So we insert D, then O, then G, and mark G as word end. Next we insert ape. Again we start at the root. And we already have a path for A and then P. So we don't need to create these new nodes. And we just add a new child E from this P and mark it as word end. And by sharing these prefixes, we are actually saving the space. Next we insert add, then app. For app, the entire path APP exists. All we have to do is mark the second P node as a word end. And finally we insert cat. And since there is no existing path, it gets its own branch from the root. And now that we have our trie, we are ready for the magic. Instead of searching the board over and over for each word, we are going to make a single pass. We'll start a search from every cell, and our trie will be our guide or a map to see if that path is worth exploring. So we start our search from the top left corner, cell 00, where we see character A, and we check, does our trie has a path for A? And the answer is yes. So we are on the right track. And to ensure that we don't use the same letter A again in the current path, we'll mark the cell as visited, perhaps by changing it to some special character like hash temporarily and continue. And from A, let's explore its neighbors. We can't go up or left as it will lead to out of bounds error. But we can go down and right. Let's say we go down first to letter P. And now our current path is AP. We check in trie, is AP a valid prefix? And the answer is yes, because A has a child for P, which can lead us to the words like app or ape later. So we mark this cell with P as visited. Now from this P, we can't go up as A is already visited. And left is out of bounds. But right will lead us to letter L. However, trie doesn't have the prefix APL, as node P sees no child for letter L. So, since we can't find the prefix, we backtrack to P and try going down, where we see letter A, and APA is also not a valid prefix. So, we backtrack from here, and notice how close we were to finding words like ape or app, where our path started out correctly for these words. But the trie allowed us to prune this search immediately. We know for a fact that no word in our dictionary can be found from this path, so we stop and backtrack instantly. And this is how the algorithm is smart, because the search is based on the path and not on a specific word. And since we exhausted the search on P, we backtrack to A and try a different path from it, this time by going right to the letter P. And now the path is AP again, which is a valid prefix. And again we can go in all the four directions. But let's say we go to the right where we find the letter P, which is also a valid prefix. And look, this time node P is also marked as a word. So we found the letter app in the trie, and hence we add it to our answer list. And crucially, we don't stop here and continue further, as we can find even longer words. So from this P, say we go to right and see letter L, and the path APPL is valid in the trie. And from L, say we go down to E, where we see the path APPLE, which is also a valid prefix. And this node E is marked as a word. Hence, we found the word apple, which we add to the answer list. And that's how our search explores all the valid paths starting from this A. And the algorithm would then do the same thing for every other cell on the board, starting a new search from this P, then the next P, and so on, to ensure no words are missed. And eventually, we would start a DFS from this A and find the word add, and another search from this D would lead us to the word dog, and this D will also lead to the word dog, resulting in the duplicates in our answer. So how should we fix it? One way can be that as soon as we find a word, we add it to our results and then immediately neutralize it within the trie by removing the end of word marker in the trie. This way, even if we find another path for the same word, the algorithm won't count it a second time because the marker is gone. The alternative to this will be using a set to store the results. But modifying the trie is a common and efficient approach. And the word cat is never found because the character C doesn't even exist on the board. So a DFS for it will never be initiated from the root. So by following the paths on the board and constantly checking with our trie, we efficiently found all the words app, apple, add and dog while pruning all the paths that lead to nothing. Now the time complexity of this approach is O of m into n into 4 to the power of L. Notice that compared to naive approach, we got rid of factor of W because instead of searching one word at a time, we are searching all words at once. And this is the upper bound, but in practice, this approach is dramatically faster. The factor of 4 to the power of L is heavily pruned because we only explore the paths that are valid prefixes in the trie. And the space complexity will be O of W into L because in the worst case, the words will not have any shared or common prefixes, like the example we covered in the naive approach. And the trie would have to store every character from every word. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on the left and Python on right. First, let's build the trie node class. It holds a children map and a word string. In Java, we use trie node array of size 26, which is extremely fast for a fixed alphabet of lowercase letters, as the constraint mentions that the words contain only lowercase English letters. In Python, we use a dictionary as it is more idiomatic way to build a trie node. In the previous problems we have seen so far, we generally use Boolean flag to see the end of word, as there we just wanted to check if the word is present in the trie, but here we also want the word which we have just matched. So we store the actual word itself in the terminal node. This is a key design choice, making it easy to add complete words to our results the moment we find it. And then comes the trie class. It manages the overall structure. It holds the root of the trie and has a clean insert method. Now let's quickly go through the insert method. It is similar to the previous problems we have covered. Here we traverse the trie character by character, creating new nodes corresponding to the character in case the node is not present in the trie, and then link it to the parent, and finally set the word attribute on the final node. Now let's look at the solution class and specifically the find words method. Here we first create a trie instance and add all the words in the trie using the insert method by looping through all the words. And after that, we go through each cell in the board and kick off a DFS from each one to explore potential words. And finally, let's look at the DFS helper function itself. It takes in the current board's position I and j and the current node in the trie we are on. And the first thing it does is handle the base cases. It checks if the current position I, j is out of bounds of the board, or if the cell has already been visited, marked with the hash. If so, it stops the search down that path. Next, it checks if the current path is valid. For that, it takes the character from the board and checks if it exists as a child of the current trie node. If not, this path doesn't match any word in our dictionary, so we prune the search and return. But if the path is valid, then we move to the current node in the trie and check if it is a terminal node. That is, word on it is not null. So if this node has a word, we found a match and hence we add it to our answer list and immediately set the word on the current node to null to avoid adding the same word again. Next, we mark the board cell as visited by changing it to a hash character. We then recursively call DFS for all 4 neighbors passing along the current node. This approach is a bit verbose, but it is very clear and easy to read. A common alternative to this is to use a loop over a directions array, which is more compact. And after the recursion, we backtrack by restoring the character on the board. And in the Python version, we have a final optimization. If a node has no children after we are done with it, meaning all the words down that path have been found, so we can prune it from the parent's children map to speed up the subsequent searches. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.